Okay, in 1.3 here we're going to talk about the trig functions. There's a few things to talk about with trig functions. Let's talk about angles a little bit first. So we measure angles from the positive x-axis, right? In math, this positive x-axis is an angle of 0, and we measure our angles from there. We like to use radians. And the reason we like to use radians is because they're unitless. They're really kind of a percentage. They're the arc length is the radius times the angle if I use radians. And that arc length is, if I have a circle of some certain radius r, and I've got this angle of theta here, then this length, from here over to here, where this is my angle theta, this is s, and that's equal to r times theta. The length of that arc is dependent only on the radius and the angle that way. If you have degrees in there, you have to multiply by like 2 pi divided by, or the angle divided by 2 pi, because you need to get the circumference of the circle in there as a percentage. But with radians, that's already all taken care of, and I've got s equals r times theta that way. Okay, let's look at our basic trig functions. So I'm going to draw a right triangle, because all of our trig functions are ratios of sides in a right triangle. We'll call this angle theta. We'll call this side the adjacent side, right? There's sides in triangles. This is the adjacent side. We'll just call it A. This is the opposite side. This is O. And this is the hypotenuse. We'll call it H. All right. So next to these angles, I've got a side next to the angle that is adjacent to that angle, right? The angle has this side as one of its bits. The angle also has the hypotenuse as one of it, but the side opposite is the opposite side. Okay, so the sine of theta it's the opposite over the hypotenuse, right? SOHCAHTOA. SOHCAHTOA. So the cosine of theta, that's the adjacent over the hypotenuse from the ka of the SOHCAHTOA. Tangent is the oa of the SOHCAHTOA. Tangent of theta is opposite over adjacent. Okay, we've got 3 more. We've got the reciprocal identities. The reciprocal of the sine, 1 over the sine of theta, is the cosecant of theta, and that's equal to the hypotenuse over the opposite. 1 over the cosine of theta is the secant of theta, and that's the hypotenuse over the adjacent. 1 over the tangent of theta, that's the cotangent of theta, and that's the adjacent over the opposite. Okay. Quick review of your trig identities. Let's do common triangles. There are 2 really common triangles. One of them is if I take a square and I cut it down a diagonal, I've got a 90-degree angle there, and I've got this guy and this guy, which are both 45 degrees, right? Okay, so I've got a 45, 45, 90 triangle. Flip it over here, 45. Well, in radians, that's pi over 4. So 45 degrees or pi over 4 radians. Okay, so let's draw that again. Put pi over 4 here. And if this is a square, I'm going to put 1 and 1 for the sides of the square. This is going to be the square root of 2. So the sine pi over 4, what was that? Sine was opposite over hypotenuse, so that's 1 over the square root of 2. That's also equal to the adjacent over the hypotenuse, so that's equal to the cosine pi over 4. And then the tangent of pi over 4 is equal to opposite over adjacent, 1 over 1 is 1. Okay. So there's one of our common, and you can compute the other three, just take the reciprocals of them. So the secant and the cosecant are both the square root of 2, the cotangent is also 1. The other common triangle that we have is a equilateral triangle. That's also a nice shape, but it doesn't have a right angle in it, so we're going to split it down the middle, just like we split the square down the middle, and we get a right angle there. And so I've got a 30, 60, 90 triangle. This one's going to be pi over 3. This one's going to be pi over 6, 90, pi over 2. Right? So I've got all of my small angles basically, pi over 2, pi over 3, pi over 4. I don't have pi over 5, but I do have pi over 6. Okay, in these two triangles. So let's see if we can figure out what the other sides of this are. So an equilateral triangle, that would be 1. This guy would be 1/2, and this guy is going to be the square root of 3 over 2. Okay. So now let's try and figure out what the sines of some of these things are and the cosines are. Sine of pi over 3, let's start with that one. The opposite over hypotenuse. It's the square root of 3 over 2 divided by 1/2, right? So that's the square root of 3. Oh, sorry, over 1. Square root of 3 over 2. Opposite hypotenuse. Cosine of pi over 3. 1/2 over the hypotenuse, so 1/2. The tangent, there we go. Tangent of pi over 3. That's the square root of 3 over 2 divided by 1/2. That's the square root of 3. The sine of pi over 6. That says this side's the opposite, this side's the hypotenuse, that's 1/2. Cosine pi over 6. Square root of 3 over 2 is the adjacent. The hypotenuse is still 1. Tangent, that is the opposite over the adjacent. So I've got 1/2 divided by the square root of 3 over 2. That gives me a square root of 3 in the denominator. So those are my 6 basic identities for the half of an equilateral triangle. Okay, I've got basic Pythagorean identities with sines and cosines. You've probably heard that 1 equals the sine squared plus the cosine squared. Okay, so that's 1. If I divide everything in this by the sine squared, 1 over the sine squared becomes, in other words, the cosecant squared. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared. The cosine over the sine is the cotangent, so this becomes the cotangent squared. Similarly, if I divide everything by cosecant squared, cosine squared, I get the secant squared. This becomes the tangent squared, and cosine squared divided by cosine squared is 1. So these are my 3 Pythagorean identities. Okay, I've got angle addition identities, and that's subtraction too. One way I remember this is my high school teacher did a little cheer that goes sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. Okay, so sine, cosine, cosine, sine, cosine, cosine, sine, 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 right? Let's see how that actually plays in with the algebra here. So if I want the sine of alpha plus or minus beta, okay, up here I've got 2 sines, down here I've got 3 sines. I need a third sine up here. Okay, so I need a third sine up there, and I need a third cosine here. I'm going to do the sines on the top and the cosines on the bottom. So I've got sine of alpha plus or minus beta is equal to, it's the sine of alpha times the cosine of beta, and then I've got plus or minus because the plus or minus is the same plus or minus there, and then I got the cosine of alpha times the sine of beta. Okay, so I need a sine of alpha and a sine of beta. I need a cosine of beta and a cosine of alpha. I need both of those involved somehow, and this is how they get involved for the sine of alpha plus beta. For the cosine of alpha plus or minus beta, same idea. I've got cosine, cosine. So I've got cosine alpha, cosine beta. Both cosines are involved. I've got this sine, which is spelled differently, so it's going to be a minus plus. Instead of plus minus, it's minus plus. So if I wanted the cosine of alpha plus beta, I would use a minus sign here. If I wanted the cosine of alpha minus beta, I would use a plus sign here. And then I've got the sine of alpha, and I've got the sine of beta. Okay, so those are my angle addition identities. If I make alpha and beta the same thing, I get the double angle identities, right? Sine of 2 alpha, that's going to be, well, if alpha and beta are the same, this is sine of alpha, cosine alpha, sine alpha, that's just the same deal. So it's 2 sine alpha, cosine alpha. If I want cosine of 2 alpha, well, that's the plus there, so I have to use the minus, so I get cosine squared alpha minus sine squared alpha. So don't confuse that one with the Pythagorean identity, right? It looks really pretty similar, but it's not quite the same. Okay. I can use the Pythagorean identity to change this up a little bit, though. I could rewrite this as 1 minus 2 sine squared alpha, or I could write it as 2 cosine squared alpha minus 1. There we go. Okay. Let's do the half angles now. I'm going to use these two guys to find a half angle, right? If I think of 2 alpha as theta, then alpha is theta over 2, and I can solve for sine of theta over 2 using this expression, or I can solve for cosine of theta over 2 using that expression. But I get that cosine of theta over 2, that's equal to the square root of 1 minus plus cosine of theta over 2. I have to do this division before I undo the squaring, so it's all over the fractions inside. Sine theta over 2, same thing except for I have a minus sign. Okay, those half angle identities are going to be useful to us for sure when we get to Calc 2, and probably sometimes useful for us here in Calc 1. Okay, last thing I want to do is the graph of a general sine function. Okay, So let's draw a graph here of some sort of a sine function. And we're going to label some of the parts. So peak to peak, that's the period. We'll call it P. Okay. Trough to peak, that's 2 times A, 2 times the amplitude. Sometimes these things might not be centered on the x-axis. Right. Let me do that so that this is maybe down here is my x-axis. Well then, wherever this center line is, we're going to call that a vertical shift V. And there's one other thing that's involved here. This is where this sine function starts. This is my horizontal shift. I'm going to call that H. It's a phase shift. Okay, so there's different parts. This is twice the amplitude. I've got this vertical shift, I've got this horizontal shift, and I've got this period. If we think back to how we had in 1.2 all of these things tied together, well, I can create these general graphs by taking a sine function, f of theta equals a times the sine of theta, well, the sine of something here with theta, and then I want to plus v to it to get that vertical shift. Okay. Here inside I need theta, and I want to stretch this period out by some factor p. Normally our period is 2 times pi, right? Because once you get all the way back around the circle, then the sine function starts over again. So I want to get a period of p, which means if I think about this, I'm going to first get down to a period of 1, which needs a compression by a factor of 2 pi. So I'm going to multiply by 2 pi to get that compression. And then to get it out to a period of p, I have to stretch it back out by a factor of p. So 2 pi over p is how much we're going to compress theta. But I also need to get this horizontal shift in here of h. Okay, that phase shift. And I'm going to subtract h because my phase shift should be a move to the left or the right. And I'm going to do that before I do the period change. Okay. So this is what our general sine function looks like. I've got my phase shift here, I've got my vertical shift, I've got my period change, and I've got my amplitude. Alright, that's it for the review of trig stuff. We'll see you guys next time.